Welcome back, Honors Algebra 2 and Algebra 2 students. We are on page 166 of your student journals, and we are talking about lesson 6.3 today, which is kind of your introduction to what a logarithm is. All right, so today we're going to talk a little bit about how a logarithm and an exponential function are related. And so I've talked about before how they're going to be, they're inverses of each other. In other words, they're kind of like the opposite of one another. So the general form for a logarithmic function is x equals log base b of y. And so you might notice that it's like the x and the y are different, right? So normally it's y equals and then something to do with x. But because this is an inverse, we're talking about x equals and then log base b of y. So we've kind of changed things around a little bit. There are going to be two different things that I want us to know. So first of all, what a log is, it's like an operation, like you would if you were to add numbers or subtract or multiply or divide. It's something you do to numbers. So taking the log of something is an operation. In other words, it's doing something to the values, right? And so it's, like if you were to divide both sides by, 10 or whatever, you're doing something to your equation. If you're logging both sides of an equation, you're doing something to your equation. So it's an operation that we're kind of applying to variables or numbers in our situation. So that's kind of what I wanted you to understand what it is. And today we're going to talk a little bit about what the graph looks like and how it's related to exponentials and so forth. There are a couple logs that we use more frequently, and one's called a common log. And so what I want you to know about this one is it's a log with a base of 10. So if you look on your calculator, there is a log button, it's right here. This is what we call common log. So when we just see the word log with no little base by it, it's what we call a common log. So see how here there's always like this base value. We call this log base, 5 or log base 2. Well, a log with a base of 10, instead of writing it as log base 10 of y, we will just write it log of y. So anytime there's a log without a number as its base, we assume that it means it's a base of 10. So that's what we call our common log. Anything on our calculator, this log button on our calculator, like I was showing you, is the common log. So it's a log with a base of 10. All right, so the next one is a natural log, and this is a log with a base of e. So we've talked about e being that irrational number, right? So rather than writing it log base e of y, we write it as something called a natural log. And so the abbreviation is ln. Again, it kind of seems a little backwards, seems like it should be nl, but I don't make up the rules, right? So it's ln is our abbreviation. And so on your calculator, you will notice that there is an ln button as well. It's actually the same button you use to get to e, except without hitting like the second. So anyway, this ln, or this natural log, just means it's a log with a base of e. So remember, your base is a number in this scenario. In a common log, your base is 10. In a natural log, your base is e. All right, so one of the things we're going to be asked to do is kind of evaluate and then switch forms of our problem. So for example, we will be going in from exponential form to log form and vice versa. So you might be asked to evaluate what a log is. So like, for example, some of the keywords or what you'll be asked to do is something called evaluate, which just means find the answer. It's like if I gave you a problem of, 5 times 4 plus 6, all raised to the 5th power. And I might ask you to evaluate that, which just means to simplify it and follow order of operations. When it comes to logs, okay, so let me give you a sample here. Log base 4 of 456. What I normally do is if I'm asked to evaluate a log, so first and foremost, we can put this into our calculators, okay? And there's gonna be a couple ways in which we can do this, but one of the ways is if you hit the math button here, so it's located kind of down from the second button, so hit math. And if you arrow up a couple times, so if you go, it's basically going to the end of that list, you will see something called log base. Now, if you have a kind of a newer calculator, which probably most of you have, you'll get this kind of template in your calculator. So you can see that a little bit better. You'll get this template in your calculator, which basically just means it kind of sets up how you're going to evaluate your log. So for example, log base 4 of 256, I would put the 4 down here, arrow over, 256, hit enter, and I get. There are going to be times, so obviously this is helpful, right? Because you can evaluate a log, like take the log of something, take the log of 256 by using your calculator. But there are going to be times when I ask that you evaluate logs without a calculator. And so one of the ways I would like you to do this is to kind of change this into exponential form. So what I mean by this is if you set this equal to like some variable. So in this case, let's just set it equal to x because we love to use our x's, right? We're going to change this log equation. So now it's an equation because I have an equal some number. We already know that this equals 4, right? Because that's what we just figured out on our calculators. But let's pretend we didn't know. So we're going to say log base 4 of 256 equals something. Well, one of the ways you can figure this out is if you change this into exponential form. So to do that, you would take the base of this log, raise it to the power x, so 4 to the x, and it would have to equal 256. So this is what we call log form. This is what we call exponential form. So what we can do is, it's harder to kind of do in our heads to evaluate a log, but if we can change it into exponential form, then there's a lot more potential for us to be able to figure out what this answer is. So now basically I'm asking you to say, okay, 4 to what power is 256? And you know that the answer is 4. So let's do another one. If I asked you log base 8 of 0.125. So again, this you could put into your calculator and get an answer, but one of the other ways that I could do this is to go ahead and set this equal to a variable. So let's set it equal to x. And then let's change this into exponential form. So take the base, raise it to whatever it's equal to, in this case it's x, equals, so this would be 8 to the x equals 0.125. A lot of times, I'm just going to be completely honest with you, if you're trying to do this in your head, a lot of times it's way easier if you think about this as, instead of decimals, as fractions. So 0.125 is the fraction 1/8. So now you have to ask yourself, okay, what do I raise 8 to get to 1/8? Some of you might already know, like you might think, oh, okay, I would just raise this to the -1 power. And if you can figure that out, great. If you were kind of wondering how to get to this, the only way you're going to go from like a whole number to an answer that's a fraction, or vice versa, if I had a fraction and I wanted to go to a whole number, is for your exponent to be negative, because that's the only way you're going to get that reciprocal action. So a lot of times what I do is I think, okay, well, if I'm going from a whole number to a fraction, I know that it has to be negative. And then what number do I have to raise 8 to get to this 8? Well, in this case, it would be 1. So I raise 8 to the -1, and I would get 1/8. Let's do a couple others. Log of 1/3 of 27. So this is another one. Again, it might be helpful if we're going to do this in our heads to go ahead and set that equal to something. Let's change this into exponential form so that we can try to figure this answer out. So what I did is 1/3 to the x equals 27. All right, so notice you're going from a fraction to a whole number. So again, whole number to a fraction, fraction to a whole number. Your exponent needs to be negative in that scenario, right? Anytime you're going from a whole number to a fraction or a fraction to a whole number, your exponent needs to be negative. So now you have to ask yourself, okay, well, this 3 is going to be kind of the deciding factor, and so is this 27. What do I raise 3 to get to 27? Well, the answer would be 3. So 1/3 to the -3rd power would give me 27. Let's do another one. Log of 64 of 8. So again, I'm going to set this equal to x so that I can go ahead and put this into exponential form. So 64 to some power equals 8. This one's a little bit trickier. And so you might have remembered when we did this in like our exponent unit, I think it was unit 5, We talked about how we could change these bases so that they have the same base, so that we could evaluate them. What I mean by that is I can rewrite 64 as 8 squared. And then if I do that, now they both have a base of 8. So now I have 8 to the 2x equals 8. So now essentially what I'm doing is I'm saying, okay, well, I got to figure out what exponents, right? How do I make these two things equal? Well, remember, is just 8 to the first power. So if I take my exponents and set them equal to each other, I know that I'm solving this and I get x to the 1/2. Another way of thinking of this is thinking, okay, 64 and 8, how are they related? Well, the square root of 64 is 8. So then what exponent would you have to raise x to in order to get that square root? Well, that's how you get the half. So either way you think about that, both of those are kind of the same idea. One was just kind of reverting back to what we did in Unit 5. All right, go ahead and find page 164 for me. All right, so on this page, what I want you to remember is we're gonna kind of go back and forth. We're gonna evaluate some more. So again, what I want you to remember is that we have kind of a relationship between an exponential form, so y equals b to the x, and then a log form, which is x equals log base b of y. So again, because these are inverses of each other, basically what we're doing is we're switching the x and y, and a logging is kind of the opposite operation of an exponential. So let me say that again. Taking the log of something is the opposite operation of an exponential. It's kind of like what you ask yourself if you said, okay, x squared equals 100. What do you do to both sides? Well, you square root. Why did you square root? Because square rooting is the opposite operation of squaring, right? So taking the log is the opposite operation of an exponential. So a couple things that we're going to really kind of focus on here is how to do an inverse, okay? And so we're gonna rewrite these, and we're gonna kind of go back and forth between two different forms of our expression. So in this one, I know it says work with a partner. We're going to kind of do this together here, but it says find the value of x in each exponential equation, explain your reasoning, then use the value of x to rewrite the exponential equation in its equivalent logarithmic form. All right, so all I'm asking you to do here is say, okay, what power to x, 2 to what power equals 8? And so most of you would probably tell me that is 3, right? 2 to the 3rd power is 8. To write this format, so this is our exponential form, to write this as a log, what I want you to start recognizing is what parts of the inverses are, like what is the inverse of what? For example, if I have an exponential with a base of 2, see how it has 2 to the x, then the inverse of it would be a log with a base of 2. So an exponential with a base of 2 is equal to a log with a base of 2. So whatever our equal sign, so like in this case, remember how when we were kind of switching them back and forth, the log base 2 of what number is going to equal x. So this is how we kind of put this into log form. So the 2 becomes your base, the x becomes what goes after the equal sign, and the 8 becomes what you take the log of. So essentially, in your equation, and I'll kind of write it up here, you're going to have log base something. So like these are kind of the components that you have, right, for a log. If you're looking at exponential, okay, if you're looking at your exponential equation, the b, I'll use this one, this base here has to be your base here. Whatever you take, whatever is this exponential is equal to is what you're taking the log of. So that's the y part goes here. And this x is what you're the answer to your log. So in terms of how we can go from an exponential equation to a log equation, those are kind of where all the parts go. All right, let's do a couple more of these just so you can kind of practice. So 3 to the x equals 9. What power would that be? You'd probably tell me that's 2. To write this as a log equation, I would say log base 3 of 9 equals x. So again, remember how I showed you before with like kind of I drew those little arrows? And I did that because it kind of helps me to rewrite it from a log form to an exponential form, but it's going 3 to the x equals 9. So if I undid this log formula, I would get to this exponential formula. All right, so some of these get a little tricky, and so I encourage you to kind of think outside the box a little bit. All right, so we have 4 and 2. So again, kind of think about what you're doing to get from 4 to 2. Think powers. What power would you have to raise x to? What power would you have to raise 4 to get to 2? Well, you might be thinking that 4, how they're related is that if you take the square root of 4, you get 2. And so in other words, we know that that power has to be a half. So this would be log base 4 of 2 equals x. All right, 5 to the x equals 1. What power must x be in order for this to equal 1? Well, remember, what power, anything raised to what power equals 1? Do you remember that one? It's the 0. Anything to the 0 power is 1. So here I would have log base 5 of 1 equals x. So that's its equivalent log form. All right, this is kind of like the one we did on the other page. 5 to the x equals 1/5. We're going from a whole number to a fraction. So you know your exponent has to be negative. And then from 5 to 5, you would raise this to the first power. Okay, so this would be log base 5 of 1/5 equals x. Okay, this one, 8 to the x and 4. So we did one like this on the other page. I was kind of showing you, we did this again in our rationals unit. Our rational exponents unit. So what I would encourage you to do is to, if you can't think of like any of the other ways that we've talked about this, to evaluate this, you would think of this as having the same base. So for example, I can rewrite 8 as 2 cubed and I can rewrite 4 as 2 squared. And then I can set my exponents equal to other and get x to equal 2/3. So it might not be completely obvious what you raise 8 to get to 4, but again, if you kind of think of it in terms of changing the base, it might be a little bit simpler. So this would be log base 8 of 4 equals x. Okay, next, what we're going to talk about. So if you go to page 165, or actually I lied. We're going to go to this page. So I'm going to ask that you grab a sheet of paper. Make this a little bit bigger for you. We're just going to kind of chat a little bit about what the inverses look like graphically. So I just called this exponential functions, log functions. All right, so if we have an exponential function, let me kind of just do a recap, right? So here's our exponential function. Let's say I have my basic exponential function. It looks like this. We'll make a growth, okay? You might also notice that every exponential function will have an asymptote. So I'm going to use a dashed line here. I'll call that y equals 0. All right, so on this one, this exponential function, I'm going to have a starting value at 0, 1. So that's my a value. So that's my starting value. My b value has to be greater than 1 because this is growth. And my y equals 0 is my asymptote. So those are all kinds of things I noticed from my basic exponential function. This is what a basic log function looks like. So it's all kind of the inverses of all of these things. So what I mean by that is, instead of having a starting value of 0, 1, we're having a starting value of 1, 0. So again, it's the inverses. We're switching x and y. So this is going to be our starting value. Instead of having an asymptote at y equals 0, we're going to have an asymptote of x equals 0. So again, completely the opposite, switching y and switching x. And so my equation here was y equals a b to the x. This equation would be y equals a log base b to the x. So what this means is this exponential, whatever this base is here, is the same as this base of this log. How the equation's going to look is it looks like this. It looks kind of like a sideways exponential function. And so it's going to have a curve, and it's kind of going to bend. It's going to approach your asymptote, but then it's going to kind of curve outwards. The reason why this happens, and this is what I want you to kind of turn your papers over and I want to show you this. The reason why this happens is because, so let me go back to my basic exponential. So here's my basic exponential. When we switch x and y, okay, so think about it. When we switch x and y, what we're doing is we're taking that graph and we're reflecting it across the line y equals x. And so when we do that, okay, think about a mirror image of this, right? So what happens is my graph, if I fold it along that line, that's what I would end up with. So I have, this is my exponential function. If I take the inverse of it, which is, in other words, switch all the x's and y's, then I get a log function. So that's what the inverse is going to look like. Algebraically, what will happen is if I have, let's say, for example, I had y equals 3 to the x. So this is an exponential function with a base of 3. The inverse of this would y equals log base 3 of x. So this is a log with a base of 3. So again, exponential with a base of 3, log with a base of 3. These two functions, if you graphed them on your calculator, would have this relationship. They would be inverses of each other. All right, let's take a look at page 167 of your student journals. And so they're kind of going over here some of the basics of graphing. You can welcome to read through any of this. What I want to do is just kind of practice doing a graph for a log. So I'm picking actually a graph of a natural log, and because I'm picking this one because I want to show you that it doesn't matter if it's a natural log or a regular log. I want to show you kind of how to do this. So anyway, a natural log is just a base of e, right? Or a regular log is a base of any other number, 5. So if it's a common log, it'd have a base of 10. When we graph these by hand, what that base is going to do is going to ultimately end up causing our graph to be steeper or less steep. So that's going to be how that base changes. So a lot of times you won't see a difference unless we graph a whole bunch of them on a grid, or if we graph them on your calculator, you would see. So real carefully, what I would like you to do is if you are graphing this, what I'd like you to do is have a starting value. So remember, our starting value is at 1, 0. So that's going to be right here on the x-axis. We are going to shift the function the same way we shift our function with an exponential. So like, for example, this causes my graph to shift left and right. So that's going to cause my graph to shift 2 to the left. This is going to cause my graph to shift up 1. So remember when we talked about that translated intercept with an exponential function? Same deal here. We started at 1, 0. We applied our shifts. We shifted it left 2 and up 1. The other thing I want to remind you about is the asymptote. So remember, in an exponential function, like y equals 3, 2 to the x minus 6. Remember, this value here, this k value, was your asymptote. In a log function, since it's the inverse, it's the h value that's your asymptote. So here, my asymptote is going to be oops, I shifted this. Oops, I'm sorry, this should say plus because I'm shifting it to the left. So my asymptote is going to be left 2. Sorry, I apologize for that mistake. Should have been a plus sign there. I just didn't cross it. So remember, your normal asymptote is at x equals 0, but this is causing my graph to shift 2 to the left because of the plus sign now, which means that now it's going to be at x equals -2. And so what that does is now I can draw in my graph, kind of looks like that hook. It's going to approach my asymptote and have that translated intercept of the point 1 or -1, 1 is my translated intercept. I'm going to show you a little bit later about how we can kind of get some a little bit more in-depth graphing when it comes to some of these functions. All right, on the bottom here, it asks us to rewrite the equation in exponential form. All I'm asking you to do here is kind of go back to exponential form. So to do that, remember, you take the base, which is 10, raise it to whatever you have over here equals 1,000. So this should make a true sentence. Okay, so if you're taking a true log equation and you're writing it as an exponential equation, this should make sense. So does 10 to the third power equal 1,000? Yes. And so all of these, so the base 5 raised to the negative 2 should equal 125. So it's kind of like we're doing the opposite of evaluating, right? We're kind of rewriting it as the exponential. This says 10 to the 0 power has to equal 1. So log form, exponential form. This says 1/4 to the negative 3 equals 64. So remember we talked about before, going from a fraction to a whole number, your exponent needed to be negative. All right, last but not least, let's look at page 168. Let's do a few of the ones on this page. So I'm not going to kind of go over a ton of these, but basically you're going to write some equations in log form. So I don't know, I'll pick number 6, for example. So remember, when you're writing in log form, the base of your exponential needs to be the base of your log. So in this case, it would be 20. What you're taking log of, so log base 20 of what? Well, you're taking the log of 1/20. So this is like you're logging something, kind of like if you were multiplying by 5. You would take a number and you multiply by 5. Well, I'm taking this 1/20 and I'm logging it, for lack of a better term. I'm taking the log of it. It's going to equal whatever the power is of my exponential. So in this case, -1. How you can check to make sure you did this correct is always easier to kind of go back into exponential form, but does 20 to the -1 give me 1/20? And the answer is yes. Evaluate these logs. So again, this is the one where what you're going to do here, I'll do number 11, for example. You would set this equal to something. So like here, you'd set it equal to x if you're going to evaluate, and then rewrite this as an exponential form. So 2 to the x equals 1/32. So I set it equal to x because I'm trying to figure out what this equals without using a calculator. And then I would take the base, so 2 to the power x has to equal 1/32. Remember, what does x have to equal? Well, in this case, because we're going from a whole number to a fraction, it has to be negative. And then 2 to what power is 32? And the answer is -5. So I'm not going to do all of these. I'd like to give you guys an opportunity to do some of them. All right, number 13 and 14 we haven't really talked about, so let me show you kind of what I'm looking for here. In 13 and 14, what I want you to understand is that anytime you have an exponential and a log with the same base, those two are kind of undo each other. It's like having 5 squared, right? No, that doesn't make sense. I'm sorry. It's like having 5 squared to the 1/2. In other words, taking 5 squared and square rooting it. These kind of undo each other, right? They cancel each other out. So an exponential with a base of 3 and a base of 13 and a log with a base of 13 cancel each other out. Those are inverse operations, just like square rooting and squaring are inverse operations. So my answer here would just be 6 if I was simplifying this. Same thing with natural log. A natural log and an e, so a natural log and an exponential with a base of e, are inverse operations. So those two things essentially cancel each other out. And then what we're left with here is x cubed. So what I'm trying to reiterate here is, again, this understanding of how the exponentials and the logs are related to each other. They're inverses of each other. All right, next but not least, let's try to actually find an inverse of a function. So let's do number 15. So what I'm having you do here is to find an inverse of a function, you're literally going to switch your x's and your y's. So let's do that. So I would have x equals 15 to the y plus 10. Solve your equation for y. So let's first subtract 10. Okay. So now you're down to this. So now you have to think about, how do I get rid of this 15? So remember what I said. An exponential and a log are inverses of each other. So to get rid of an exponential with a base of 15, you have to log base 15. Because if I log base 15 both sides of my equation, right? If I log base 15 both sides of my equation, those cancel out. Again, it's like, 5x equals 25. You divide both sides by 5. Why? Because it's inverse operations. So how do I get rid of this 15 here? I have to log both sides because this is an exponential with a base of 15. So the inverse would be a log with a base of 15. So then my final answer would be log base 15 of x minus 10 equals y. Notice I put this in parentheses, and the reason why is because I'm taking the log of the entire thing. I don't want you to think of it as log base 15 of x, and then you're subtracting 10. But it's log base 15 of x minus 10. All right, number 16, let's do this one. This is where you're given an exponential. I want you to find the inverse. So here, what I'm going to have you do, again, switch your x and your y. Okay. And let's solve for y. So let's add 8 to both sides first. Okay. So now you have to ask yourself, how do I get rid of a natural log? So this is a log with a base of e. The inverse of a log is always an exponential with the same base. So the inverse of a natural log would be an exponential with a base of e. Whoops. This should say natural log of 2y. So I'm going to take an e to both sides of my equation because the inverse or the opposite of a natural log, which is a log with a base of e, is an exponential with a base of e. So I'm going to do an exponential with the base of e to this side, an exponential with the base of e to that side. And again, what happens is my exponentials cancel out and my e cancels out, and I get e to the x plus 8. So this equation is the inverse of that one. All right, let's do a graphing one and then let's call it a day. All right, so we did one where I graphed the natural log, right? So let's draw in my axes. Let's just kind of use this. So how you would start by graphing a log is you would start with your starting value, which in this case is 1, 0. It's your a value, so if there was a number out in front, but in this case there isn't, or it's just 1. Then you would apply any shifts. So what this means is we're moving left 1. So instead of here, I'm going to end right here on the origin. So that's going to be my translated intercept, 0, 0. Remember what I told you before, the asymptote is always this value here. So if the asymptote is at 0, 0, the asymptote was at x equals 0, I would shift that one to the left as well. So now my asymptote is at x equals -1, and now I can draw in my graph. Now I just kind of drew in the graph. It would be helpful if you actually found some points. So we're going to get to the point where I want you to be able to graph like several points. So we know that we graphed 0, 0, that's this one. Let's find a couple others. Let's say, for example, I wanted to do 1. If I plugged in 1 here, I would get log base 2 of 2. Well, what does this equal? You can either A, punch it into your calculator and tell me what you get, or you can evaluate this like we did on the other problems on the other page, where you set it equal to x, and you say, okay, 2 to the x equals 2. Well, what does x have to equal? It has to equal 1. So the point I'm looking for is 1, 1. Another one that would work out well, and again, if you had a graphing calculator, you could just, you can use decimals and so forth, but one that's going to give us a nice answer would be 3. And the reason why is because I would do log base 2. 3 plus 1 is 4, right? What is log base 2 of 4? Well, about it. 2 to what power? 2 to what power equals 4? And the answer is 2. So 1, 2, 3, 1, 2. So I was a little off on mine. This is more the trajectory of my graph. And that would be your log function. All right, we're going to get some more practice with graphing logs, but you're going to want to obviously practice some of this on your own as well. Come to class with any questions, and that's all I have for now.